All right, so we officially kick off Mod 4 today. Before we get into PCA, our first thing, and actually let me just have this set up so I don't have to do this later. Before we get into PCA, I wanted to give you all like an overview of what this mod looks like. And to start, to kind of like make sense of like why this mod is structured this way, I think it is also worthwhile like taking a look at the final project. With this final project, slightly different from all the past final projects we've done, you have the choice of 4 different kinds of problems for your final project. So as you can see here, it's going to be either time series, recommendation system, image classification, or NLP, natural language processing. And each of these actually does have a provided data set. If you want to do one of your own data sets, you can let me know too. But the fact is, there are these 4 very, very different topics. So a lot of students actually treat this mod. I mean, I also kind of suggest this. This mod you can treat as like an elective mod where you really choose to focus in on what you're interested in. So these main ones, time series, rec systems, image classification, and NLP, if you take a look at, all of the sections here, 36 is recommendation systems, 37, 38, time series, 39, NLP, 40, 41, 42, neural networks, and neural networks is where image classification is. So that's kind of like the structure of like the bulk of mod 4. The other sections are kind of not that they are not useful, they are like just little parts that you can incorporate into your project. So today's and Monday's PCA and clustering, these are unsupervised learning elements that, again, I'll go through what that is, but these are things that you can incorporate in pretty much any of your projects. And when we go through them and as we go through like the other section, I can talk about how you would incorporate these if you would like to, but it's not a must that you incorporate these into your projects. Then there's big data in PySpark, and then there's operationalizing code with AWS. So I would group those 2 sections together because neither of these, big data or AWS, neither of these are going to use for this mod project or your capstone. You're not going to be using them. It's just something that's good to know and good to be aware of. So I'll still be going through some of the material, but I will say big data and PySpark, that's the one that a lot of people skip. And I think in 2 weeks when we get, next week when we talk about it, I'll explain why. And then this AWS, I'm actually not going to be doing a study group on AWS. And the reason for that is because when you click into these lessons, they're actually linked to the AWS tutorials that teach you exactly how to use their platform. And I don't think it makes sense for me to just go over the same steps. But again, like during any of the office hours or one-on-ones, happy to answer questions if you're running into issues with that. But yeah, all the instructions on how you use these are in there. And basically that AWS section is about like, how do you do like a machine learning project on AWS? So no new concepts, just a new platform. So yeah, that is the structure of mod 4. While we're going through the material, a good idea to like, well, I think maybe before we go into material, what are you drawn to first? And what are you more interested in? Maybe you can even rule one or two of them out. If you know that you definitely don't want to work with neural networks, you can rule it out. So that will help, streamline your progress in this mod. And with,
yes, can I ask a question?
Yeah.
So just one thing I'm wondering is,
yeah,
we haven't yet gone over any particular softwares or whatnot that I imagine a lot of us would use once we take on roles in data science. So things like AWS or Tableau or something like that. My one question for you is it really just the case where, we would go through this program and then once we actually get into a particular role, then we would need to learn those softwares? Is that like the general way it works, or would we need to learn before we get, like, would I need to go do some self-study and learn certain things and get certain certifications in particular areas before kind of getting a role?
Yeah, that's a good question. It is honestly very, very, it depends is the short answer. So a lot of these softwares, like working with AWS, AWS does have certifications. I will say like a lot of data scientists from our program who become data scientists, I would say like less than half of them end up using AWS. And if they do use AWS, it's something that they have like companies have training programs for. So AWS and like cloud services and some of the stuff that we'll talk about with PySpark next week are of that nature. Like we'll see in PySpark that like if you really want to be like a PySpark expert, you would need like another course to be an expert. But these things, it's just good to be aware of it so that, you know, if you're a data scientist and you are on a team with somebody working on something like that, you would know like roughly what kind of information they need. With respects to like things like Tableau, Tableau is, if for those of you who don't know, Tableau is a dashboarding software, a visualization software. That's basically, it's like a non-technical visualization software. So you just need to be aware of all the functionality. Things like Tableau, in the same group as Tableau, there's also one called like, oh, what's the one called? It's like something business. I don't know. I know one is called ClickSense. There's one, I forget. It's like very similar, basically any visualization software. I will say if you have a background in coding, picking up those softwares is it's a lot easier to pick up those softwares with a background in coding. You can take courses on these. They are available. There are like Tableau courses, but I will say like, if you're used to, you know, working with, if you can work with Seaborn and Matplotlib, picking up Tableau is very, very easy. And also later, during capstones, I'll be going over Dash, which is like a Python dashboarding software that you actually code out with Python. If you can do that, Tableau will be a piece of cake. But with Tableau, it is something that, you know, it appears on job listings a lot. I would say there are free trials that you can download and just like play around with, and you'll see it's really just like you'll take the column of data you want and drag and drop it to the axis. It's just like, yes, more of some of the more advanced features, like how do you like, you know, have a system that continually updates. Those are things that you can find on YouTube actually. So I will say in terms of like the learning curve for those things, visualization softwares, not as steep as something like data science. And if you have this background in data science, it'll be a lot easier to pick up. Hopefully that answers your question. You should be doing some self-study always, I think, as like someone in the tech field, just because things are always evolving and changing. But yeah, I think with a background in this stuff, things are made easier.
For sure. All right. Thank you.
You're welcome.
One quick question. So
Yeah.
now with all the sections, right? What else? Yeah. So can it be said, right? Prepared like, okay, section 35 and 36, if you are going to focus on right up this project,
Yeah.
section 38 and 39, if you're going to focus on this project.
Yeah, that's exactly how you should do it.
Okay.
So, I mean, I will say, please come to all the study groups so that you are at least aware of some of the terminology, and at least like you would have heard me say some of this stuff before, so it's not completely unfamiliar. But yeah, you definitely will do a deep dive in whichever one you want to do your project on. Maybe whichever one you think you want to do your capstone on, maybe you can also do like a moderate dive now. Also, one thing I wanted to point out is I will actually be talking about some of the stuff that is in the appendix. So more time series, you can see here, time series is really an extension of here, and I will talk about these. There's also convolutional neural networks, which is what you use for image processing. I will also talk about these. Transfer learning and deep NLP. Transfer learning is also part of image classification as well, actually. And deep NLP, I will be talking about this stuff too, just because I want you all to have the exposure to more of the depth within these electives. So if you look at the calendar, I've actually like expanded, like natural language processing is going to be 2 sessions, and then neural networks is going to be like, I think 2 full weeks of we're going to be talking about neural networks. So something to keep in mind when thinking about, you know, what do I want to do my mod 4 project on, definitely consider what you might want to do your capstone on. I know it's still a bit away. It's technically like 8 weeks away. But for your capstone, that can help determine, maybe you want your mod 4 and capstone projects to be very, very different. So you have a variety of things on your resume, right? So if you want to do like a big project on like a recommendation system, maybe don't do that for your mod 4 project. Or maybe you want to do like recommendation system for mod 4 project, but do like a really complex one, a much more worked out one for your capstone. So it's really up to you to think about. It's kind of in a way also like planning what's on your resume. But yeah, those are things that I also want you to keep in mind. If you ever wanted to talk about like ideas that you have for this project or capstone, it's a good time to start thinking about it because we're nearing like the tail end of the course too.
So
But yeah.
capstone involve a live site, website kind of thing where like you just have your system uploaded and like if anybody can go and just check the predictions that are.
Yeah, so that is not a necessity for capstone, but a lot of students do that for capstone, but it's not a must.
Okay.
Yeah. And like the underlying models that are on that web page, is it a recommendation engine? Is it a classification model? Is it like NLP classification project? Yeah, we'll talk about that in more detail when we get to the capstones for sure. But yeah, before we really dive in, and PCA is not going to take too long, so don't worry about it going late. But yeah, before we get into it, any other questions about like this mod as a whole? Some of the things to look out for, and like whenever there's something that I think is important for y'all to consider, I will always mention over and over again. All right, let's get into it then. So today's topic, we're going to be talking about PCA. And quick overview, we're going to talk about unsupervised learning because everything we've been doing so far is supervised learning. So we'll talk a little bit about that and what PCA is. We'll talk about why we will want to do PCA, how it works, and how we evaluate. Oh, and before I forget, let me just pull up the documentation so that I have this for reference. All right. So unsupervised learning first. What we've been doing up till this point is we've been doing supervised learning problems, right? We've been classifying things and we've been running regression models, all of this to predict some sort of outcome variable that that we want to label, or like for classification, we want to label, or for regression, we want to predict. The data that we use for training supervised learning problems, all that data is labeled, right? Like, when we were trying to build a model for housing prices, we had the actual price that we always compare with our predicted price. And with our classification problems, they were labeled with like your zeros and ones, and you would compare those results to, from your predictions, are the zeros and ones correct or not? And so those are supervised learning problems. You want to make predictions on your labeled data. You want to see if your model is learning patterns of, trends in your regression or, patterns in your classification. The difference between supervised and unsupervised learning is in unsupervised learning, there are really no labels. One common example, I think the easiest example to talk about unsupervised learning is with clustering. And clustering we're actually going to talk about on Monday. But how clustering works is, imagine you have, and the most common example is, imagine you have a bunch of basketball players. And now in basketball, you have like your, please correct me if I'm wrong, but you have 5 positions in basketball. And like, you decide who's in what position based on, maybe like the style that they play, or like, I don't know, their height sometimes, stuff like that. But there have been some people saying that, oh, the way of us grouping these players into these 5 groups might not be the most efficient way to group players. Like maybe you want like a different way of grouping players to like maximize like the strengths and weaknesses of everybody. And so with that, you can apply a clustering problem to regroup all of your players based on, maybe their stats, their like height, weight, maybe how long they've been playing, stuff like that. And maybe you're going to mathematically regroup them into, for example, maybe you want more granularity. So maybe you regroup 5 groups of players into 10 groups based on their stats. And so with clustering, it is unsupervised because you won't know which group what player will be in until the clustering is done. And then once you have your clusters, your groups of 10 players, like your 10 different groups of players, you'll look into each group and say, all right, all these players seem to be like good, I don't know, good defensive players, for example. And then you would label those groups then. Does anyone need any clarification on that example? So the thing is, we're only telling the algorithm how many groups of players do I want. The algorithm will run and then group the players for you. That's why it's unsupervised. And it's a tough thing about unsupervised learning, especially with clustering, is how do you what's the word, evaluate how good your clustering is? It's a lot harder to do that because there are no labels and it is unsupervised. Questions on supervised versus unsupervised? All right, PCA, what we're talking
Well, I have a quick question.
Go ahead. Yeah.
And I don't even know if it makes a whole lot of sense, but anyway. So what I'm thinking is if you have an unsupervised learning clustering situation, and then the algorithm learns, is it after it goes through that that process of learning, are there labels then?
So automatically, no. You actually would have to go and look into your clusters and label them yourself. Yeah, and we'll talk about that on Monday, because Monday's where we will be talking about clustering.
Got it. Okay, awesome. Okay, cool.
Yeah, awesome. So in a similar vein, PCA, which is what we're talking about today, is also unsupervised. And we'll talk about why that's unsupervised in a little bit. Something else that's really cool that I will mention, LDA. We will get to that when we talk about NLP. LDA is also unsupervised. And LDA is very exciting because basically if you have like a bunch of, let's say you take all the articles written by the New York Times in the last 5 years, LDA will sort of like group your articles together based on topics that it learns and sees. Like, all right, let's say you say, I want to look for the 5 main topics in New York Times articles over the last 5 years. You would put your stuff into an LDA model and it'll help generate these 5 groups, and you'll have topics associated with each article. And depending on how many groups you ask for, the topics can be very broad or very like specific. And we'll talk about that when we get to NLP, so don't worry about that for now. But yeah, that's supervised versus unsupervised learning. With PCA, PCA is a form of dimensionality reduction. I think I had mentioned it a couple times, like, you know, when we were getting into the Mod 3 project, but dimensionality reduction is basically when you have a lot of columns, because each column is a dimension, and you want to just, you know, compress 100 columns down to 10 columns. It could be maybe because, you know, you want your models to run faster. That's one reason to do dimensionality reduction. Maybe you want to visualize your data, and because we can only see in 2 or 3D, you want to like compress your number of columns down to 2 or 3 so we can visualize. Those would be instances of when you might want to use dimensionality reduction. PCA is unsupervised because we can only tell it how many dimensions to reduce to, and we just trust the model, we trust the algorithm and the math behind it, that it will create these new columns the right way. And how that is done, I'll talk about as well. So PCA, it reduces the dimensionality of the feature set into however number of principal components. So each new dimension is called a principal component. And the main thing that it's trying to optimize for is maintaining the variance of your data. And so the variance of the data might sound very, very abstract at first, but we actually talked about variance of your data when we were talking about linear regression. If you remember R squared, you know, R squared is how much of your variances your data is explained by the model. So basically with all the changes in your data, all the different patterns of your data, PCA wants to maintain as much of that variance as possible, as much of that like range of your data as possible. So yeah. And each principal component, so each of the new features are actually linear combinations of all the original features. So let's say you went from 100 features down to two features. Feature 1 or principal component 1 could be made up of like, you know, 0.5 times original feature 1. 0.2 times of original feature 2. So it's just like a linear combination of all of your original features. So if I have 2 principal components, each of those principal components have like 100 different parts that are made up of the 100 old columns. Does anyone need to clarify anything about that?
Well, yeah, I suppose like for like the car crash data, which I now worked on. So suppose you have like weather and road conditions and speed limit. So how would that be reduced into
Yeah,
you know, principal components?
exactly. So yeah, I know that project had a lot of features. So I think if you were to like dummy variable everything, you would end up with like hundreds of features. Is that right? Or maybe even thousands, I'm not sure. But basically you would pick a number of principal components. Let's say you just wanted your models to run faster. Maybe let's go with like 50. So each one of the 50 new principal components is going to be made up of a linear combination of all the rest. And how these linear combinations are, how you come up with what linear combination, I'll talk about in, I think, the next slide. But yeah, basically the whole idea of maintaining variance, if you have a feature that is pretty much constant throughout your data set. So let's say in that car crash data set, every day it was rainy. If you have that one feature that is constant throughout, it doesn't have much variance. It literally has 0 variance, so it doesn't change. So PCA will see that, all right, that feature doesn't help with variance. So that means in our principal components, you likely will have like a low amount of that feature. So you probably will have like 0 times the weather condition, if that makes sense, just because that feature doesn't help with variance of your data. Whereas if you have a feature that has like a big range, like maybe like speed limits, you have a big range of speed limits, it's more likely that your principal components will have a higher amount of speed limit. And we'll get into a little bit of like, I'll talk on a high level about how that calculation is done. But any questions before we move on? All right. Next up, why and when do we use PCA? So one thing to start being aware of, and I think some of you have already faced this issue, the curse of dimensionality. As we have more features in your columns, data points become more sparse. And I know we haven't really thought about sparsity of data in this way, but you think about it, let's say I had 2 data points on a 2D surface. If I have 2 data points on a 2D surface, they have some distance. If I were to like expand my dimensionality into like 3D, and let's say like these 2 points are like, okay, not on a flat surface, but they exist in 3D space, the distance between the 2 points will just get bigger by way of just having more dimensions. And that is basically derived from like Euclidean distance. There is a lab that actually walks through and shows you the calculation of as you increase dimensions, why does distance increase? So yeah, it makes it sometimes more difficult to implement some machine learning models, right? With more dimensions, you can imagine something like k nearest neighbors. You would have to calculate distance in more dimensions. In something like, all of your tree models, you're looking for the best split across more and more dimensions as you have more columns. They will just take much longer time to run. So that's the curse of dimensionality, the fact that the more columns you have, the longer things will take to run. And not just time complexity. So the longer it takes to run, that's time complexity, but there's also space complexity. You have to save these values across more dimensions. Like, for example, in k nearest neighbors, you are actually saving all of the distances, and sometimes you're also saving like coordinates. Literally, the more dimensions you have, the more coordinates you have, and that just will take up more space in memory. So when to use PCA? One, when you have a lot of continuous features. You can actually use it with categorical as well, but it tends to work better with continuous, just because if you think about variance makes sense when you have continuous features. Categorical, the variance is really more of like a proportion of like your zeros and ones. PCA also works really well with clustering. or very computationally heavy ML algos like SVM. And I think some of you were like, I think one of the algorithms that most of you ran and were like, this is taking forever, is like, if any of you did like a grid search with XGBoost, that takes a very long time to run. And that's because you have a lot of columns. XGBoost is also like by itself a very, very computationally heavy algorithm because, you know, you're boosting and running subsequent models. So if you just have fewer columns, it will run faster. I will say with PCA, you also do tend to lose some information, and we'll talk about that like information loss at the end as well. But yeah, next slide is going to be about how the calculation of PCA works. So any questions before that?
Yeah, I'm kind of wondering, given, or, you know, if we use this in order to like run a model that's complex and would, you know, take too much time or space or whatever.
Yeah.
I guess I'm wondering, what is then the meaningfulness of each variable? Because we've kind of like shrunk like maybe 10 into 1.
Yeah, that's a really, really good question. So if you're using this in your model and like, you know, you get your feature importances, for example, and they're like, all right, your most important feature is principal component number 2. But what does that even mean, right? Something that I actually didn't plan to talk about it, but they should have it in here. Within, so let's say you did PCA on your data set and you did your feature importances and it tells you PC2, principal component 2 is your most important feature. What you can do here is within your, within each principal component, you can find out the makeup of the principal component. And so within those principal components, so let's say PC2 is made up of like 0.5 times like number of minutes used and like 0.25 of like number of, I don't know, number of customer service calls, for example. I'm using the churn example. You can actually find that out through here, through the components. And I believe in the labs, they also walk through how you can extract that information. And so because, you know, a specific component is made up of like a combination of a bunch of your other features, you can use that information and like basically, what's the word? And basically infer that, you know, those are important features. But yeah, that's a great question. I believe, I hope, yeah, I think in the labs they should talk about it. Yeah, it should. If not, I can talk about it during like office hours or something. Yeah, any other questions? All right, so let's see how PCA works. So PCA works through a purely linear algebra process. So principal components are found through doing eigen decomposition of the covariance matrix. So the covariance matrix, I don't think we call it a covariance matrix when we've actually seen this a bunch. But basically, you know, when we were doing linear regression and we do our df.core, and you get all the correlations between all your features with each other, that is your covariance matrix. And that is that is what a PCA algorithm uses to find out what your principal components are. So eigen decomposition, don't worry about that word for now, but in essence, what eigen decomposition is doing is it's taking any matrix and it's going to decompose it. And so it's going to represent one matrix as a product of 3 different matrices. And that is useful because one of the resulting sub matrices will tell you the principal components. That process, if anyone has taken a linear algebra course, you have to learn it, but at like the very end of the semester. So it's quite rigorous, but the machine does it all for you. But wanted to talk really quickly about the process. Before you perform PCA, you do have to recenter your data such that the means of each feature are 0. And that's very, very important, that the means of your feature are 0. So things to think about here, what kind of scaling should you do? You want a scaler that will center your mean at 0. And so typically it would just be the standard scaler, because standard scaler centers your mean at 0. It just finds the z-score of everything. Min-max scaler, something like min-max scaler will not center your mean at 0. So take that into account. once you have the covariance matrix, doing that eigen decomposition of the covariance matrix. And the covariance matrix, if you remember, the dimensions of a covariance matrix would just be number of features times number of features. So when you decompose that, you will get some eigenvectors. And eigenvectors is basically like the matrix, one of the component matrices I was talking about after you do this decomposition. So these are eigenvectors, and eigenvectors are sorted. And once they're sorted, all you have to do is just multiply them by your data points, and those are your principal components. So it's actually, the hard part is getting the eigenvectors, but then after that, you're really just multiplying that by your recentered data. But good news is this entire process is done for you with scikit-learn. I'm going to show you all the code, but any questions about this?
Yeah, I have a question.
Yeah.
Just more really to be clear. So
Yeah.
Is it that the like each eigenvector is a sub matrix?
Oh, good question. So if you remember, vectors are like one dimensional, right?
Mm.
So this resulting matrix will have a bunch of eigenvectors.
Got it. Okay. So then when you refer to sub matrices, what was that in reference to?
Oh, that's when you do eigen decomposition of the df.core, you end up with like a few matrices, and what the other ones mean, not that important, honestly.
Oh,
but,
okay. So
yeah.
Okay, got it. So it's covariance matrix covariance matrix and then some other matrices, and then we're focusing on the covariance matrix and it's gonna work with that.
Other way around. So the covariance matrix is going to be made up of, you're decomposing the covariance matrix.
Gotcha. Okay. Gotcha. Yeah. Okay.
Mm-hmm.
Yeah, for sure. So you take the covariance matrix, decompose that, and then you
eigenvectors is one part of
eigenvectors as one part. Gotcha.
Yep.
Okay.
Yeah, that's right. This eigenvector, the dimension of the eigenvector matrix will be the same dimensions as the covariance matrix. So let's say you have like, 100 features. Your eigenvector matrix will be 100 by 100. And then if you want two principal components, you just have to take the first two columns. And then those two columns will basically be, you multiply each feature by the value in those columns, if that makes sense. So let me actually draw it out. Oops. So your eigenvector matrix ends up being a square, right? And imagine you've already sorted this, and each vector is going to be like red. I honestly forget which way it doesn't matter, but I forget if it's like columns or rows, but I think it's columns. But anyways, imagine these are your eigenvectors. They're columns in your eigenvector matrix. So each eigenvector, if you want two principal component, each eigenvector is going to have 100 values from your 100 original columns. And so maybe after decomposition, maybe you end up with like your first couple of numbers being, and let me just draw that out so that we have it for reference. Maybe you just have like 1, 2, 3. Let's just do this to be easy. Usually it's like a decimal. So with your 100 features, all you have to do is for the first component, it's going to be 1 times your first feature, 2 times your second feature, 3 times your third feature. And that's how you end up with your new principal component. I will say, if this PCA mathematically is one of the hardest things in our course. So if it doesn't make sense, it's okay. I'll send out a bunch of resources that help with understanding this process.
Okay, appreciate it. Well, just quick question.
Yeah.
You said 1 times your feature, 2 times the feature. What would that value be for that feature?
Oh yeah, so each of the is literally your data point. So let's say you have like one row of data. One row of data will have 100 values, right? Because that was your original data. And basically, for your first principal component for that feature, for that data point, will be like 1 times whatever feature 1 was, 2 times whatever feature 2 was, and
gotcha.
Keep doing that for all 100. So that's how you compress 100 values into 1 value. And then you probably have like a different set of numbers in the second principal component, and then you multiply that out. That's how you get your second principal component.
Gotcha. Okay.
Yeah.
One quick question. What happens when you add features and then like there are like the rows keeps on adding, right? Even when you add features,
When
right?
you're
The columns are more. So
when you're adding
I mean
features.
yeah, and after that, like if we run, then what data points will it select? It will be selecting the
So
original data points without
yeah.
the
So
features.
PCA only happens one time. So well, by one time is I mean like you would want to already finish all your feature engineering and make sure you have all your features set before you do PCA.
Yeah,
Does
but
that
then
answer your question?
my question is like if once we add all the dummies and all the other features to right, then the original data right is possibly not the same what we have created.
Yeah.
And then when you're checking the covariance from there, in that case, how can we be sure of the prediction later on when we do?
So okay, I think this will also tie in with what I'm also going to talk a little bit about the documentation and how you work with it in scikit-learn. But
Okay.
but yes, before you do PCA, everything has to be numerical already. So you won't even do PCA until you've already done your like get dummies, you've already like one hot encoded, cleaned up all of your data and all of that. If you have new data points, how do you turn those into PCA, right? So that will lead me into talking about scikit-learn. So PCA actually works very, very functionally. It works very similar to like how SMOTE works, how your standard scalar works, how any of your transformations work. Because PCA is also something that it depends where you're using it. If you're using PCA as part of your modeling process, you also will have to like, fit transform on your train and then transform on your test. So let's say you're doing this in your modeling process. You just want to feed in only 3 dimensions into your model rather than 100. What you can do here is how you do PCA, and let me zoom in so y'all can see. Very, very similar to like all the other scikit-learn things we've done. You first have to instantiate it and tell it how many principal components you want. And then you fit it to whatever your X data is. And this X data is your already cleaned, already completed data set. And so when you fit it onto that, you can also do a transform. I don't think they have an example here, but there's examples in your labs. You can do a fit transform to just transform the dimensionality reduction on X. And then on your test set, you're going to just do your transform, your dimensionality reduction to X. So that's how you would apply your PCA to like your test set, for example. Or if you have like unseen data points, you can also feed them through the transform. Now that we are on this page, you can do your, just want to go over a couple of the methods, fit and fit transform. That's how you like have it learn what the breakdown of the principal components are. You can also do a transform after you fit it. Also, you can inverse transform, which is pretty cool. So let's say you did PCA and then you want to like bring it back. Oh, actually, that's a really good point. If you want to like see your important features, you can do an inverse transform. I completely forgot about that. I think Sawyer had asked that question earlier. If let's say a certain principal component ended up being the most important feature, you can just do an inverse transform and bring it back into original space just to see what that looks like. Yeah. Any other questions regarding like, I will say for this part, like the implementation of PCA, I do recommend doing the labs if you are interested in maybe applying PCA in a future project. All right.
One question. Will the negative numbers affect?
Negative numbers are
Here.
okay. Negative numbers are fine with PCA.
Okay. Okay. Thanks.
You're welcome. Oh, something that I wanted to really quickly check to see is if it's been mean. Sorry, guys. I know I mentioned that you want to scale it to 0, but I believe you don't actually have, I believe the scaling is done within PCA. So you don't have to scale it on your own first. I believe that within the algorithm, it does the scaling for you. So in here, where I talk about recentering your data, this part is done within the scikit-learn algorithm. So you don't have to first scale it. All right.
But technically, would you like it? I'm just thinking about this conceptually. Like if you scaled your data and you ran it through PCA, it wouldn't change it, right?
Yeah, it should be fine.
Okay, got it. Okay, just wanted to make sure. Okay, cool.
Awesome. All right. Next thing, the question that may be on everybody's minds, I don't know, is let's say I have a really big data set and I just wanted to lower the dimensionality. How do I figure out what the best number of dimensions is, right? Like if I have like 10,000 features, which is very, very possible, and especially like in a project like NLP or in image classification. NLP, every word is a feature. In images, every pixel becomes a feature. So in those situations, what's the best number of features to use as PCA?
Could you do a grid search?
Technically, this is kind of like doing grid search, yeah, but because there's nothing to really test against, you know how grid search you always give it like a metric to solve for,
Right.
but in a very, very similar way. With PCA, the only thing you're really tuning is the number of components. The rest of this stuff doesn't really matter. These are just different solvers. Honestly, I've never been in a situation where I've had to change anything, but none of these really affect the PCA because PCA is a very mathematical model. It's literally just feeding it through like a series of math formulas. So the only thing you really have to tune here is end components. And in a very, very similar way to grid search, we are looking to maximize, and I should always forget to add labels to this graph, but because I'd mentioned, PCA is looking to maximize the variance of your data, right? You don't want to like lose all of your information when you compress all your features. So this graph, and I'm gonna just quickly put some labels, explained variance. So on the y-axis, you have your explained variance. On the x-axis, we'll have your number of principal components. All right, so this is what the labels should say. And so here we're looking at, all right, as we increase the number of components, how much variance in our data is maintained. So they'll take the variance as a ratio of the total variance of your entire data set. So with this, you can assume that, let's assume that this data set had like 70 features and you wanted to pick, all right, where's a good place to lower my dimensionality to? And there are many, many things to think about when you're working on this process. First of all, you want to maintain your variance as much as possible. So let's say you have a little bit of leeway, a point where your variance is maintained is, let's say, around like 45 principal components. Our variance is pretty much the same as it was with all of my features. So maybe you could say, like, if 45 is a reasonable number for you, let's go with 45. But let's say you are constrained even more. Let's say like your model just takes a really, really, really long time to run. Maybe you just have like a lot of rows as well. I want to get my features as low as possible. So let's say I want to maintain 90% of my variance. 90% of my variance, let's say, I think that's around here, will go down to like 20 principal components. And so you can see the fewer principal components we have, the less variance you maintain. I mean, because it's impossible to maintain all that variance in a few number of columns. But yeah, you can see as you increase the principal components, the explained variance sort of plateaus off at some point, right? Like going from like 1 to 2 principal components, there's a great increase. And then as you like increase from like 30 to 40, 40 to 50, it kind of plateaus off towards 1. So there are a lot of things to consider when choosing your principal components. Like think about what you're constrained by. Are you constrained by you know, literally if you want to like visualize something, you are constrained by 2 or 3 components. If, you know, if something about like your model runtime, you don't want your model to run quicker than like 15 minutes. Maybe you test like different numbers to see what brings you below 15 minutes. So yeah, any questions about this? All right, well, this is the last slide that I have. PCA, useful, like the situations that we have come across so far that it would be useful for creating visualizations. Let's say you want to really visualize your like 100-dimension data set. You can use PCA, lower it down to 2 or 3, and plot a scatter plot. And you can have like your different classes and different colors. That'd be pretty neat. I can actually show an example of one of my projects where I did that.
Yes, quick question.
Yeah.
How would, so let's say you had a data set and you did PCA and you looked at that variance principal component curve.
Yes.
How would doing some smote data impact that?
Oh, that's a good question. Smote data. So smote data. Oh, that's a really good question. If you have smoted your data, the variance that you're comparing to will be the variance of your smoted data. So it's kind of like in relation to. So it's not you can do PCA before or after your smoted data, and you should get somewhat similar results.
That's what I was thinking. So it wouldn't change the variance relationship.
Yeah.
With
I don't imagine that it'll
principal
change
component.
it by much. Yeah, I don't imagine it'll change it by much because smote also creates data points within the domain that is already there. Yeah, but that's good instinct. Yeah.
Right.
But yeah, just really quickly to show, these are visualizations that were made. This is like a 5,000 column data set that is reduced, which is why the shape looks so weird. But you can see here, this was my classification project, and like, you know, you can sort of see some separability here. So yeah, that's an example. If you wanted to use PCA for visualizations, that's how you would do that. And then yeah, if you have a model that's taking a really long time to run, I actually used this for SVM when I had a data set with a lot of rows, and it sped up my modeling process by quite a bit too. Yeah, any other questions to close out? Sounds good. On Monday, we'll be talking about clustering, another unsupervised learning problem. All the material, I think through the next week, I already put up on your repo, just in case anyone wants to like take a look and see what that's all about. All right, if there is nothing else, I will see you all on Monday or at Tomorrow 101s if any of you have, a couple of you have Tomorrow 101s. So I'll see you then.
Okay.
All right, good night, everybody.
Right.
Good night.
Okay.
Bye.